We now will discuss a few problems on Boyle temperature. The first problem is that calculate Boyle temperature from the following data. Atmosphere, liter square, mole square, which is the unit of the Vander Waals constant A, this is B, and R is given to be and another set of data is given according to which the value of A is so here we have bar, which is the unit of pressure, as against atmosphere, which we had in the first problem. The value of B is given as we come to the answer of the first problem. Expression for Boyle temperature is given by Tb equal to A by Br, and let us put the values. The value of A is this is B, and the value of R is this one. This atmosphere will cancel out because of this atmosphere. L and L will cancel this L square. Mole square will be cancelled by mole into mole, and only K, that is Kelvin, will remain. So what we have is and this gives on evaluation it can be verified or checked. Now the second problem, as before we just put the values. The value of A is and that of B is and we have to put the value of R. As before, these bars will cancel, L square and L square in the denominator will cancel, mole square, and here also we have mole square, so they will also cancel out, and we only have Kelvin. On evaluation, what we get is 426 Kelvin. So these are the Boyle temperatures from the given data. We move on to the next problem. The next problem states that show that at Boyle temperature the second virial coefficient vanishes. Let us go to the answer. The second virial coefficient occurs in the virial equation of state. So let us write down the virial equation of state, which is where Z is compressibility factor, A, B, C, D, etc. are virial coefficients, B is the second virial coefficient as indicated in the question, Vm is the molar volume. So A, B, C, D are first, second, third, fourth virial coefficients, and they represent interaction between molecules. Of the real gas. Let us write down the Vander Waal equation of state. According to which and we have written it in terms of molar volume. This gives us so P is let us now consider the compressibility factor Z, which is the ratio of PVM and RT, and let us put the value of P RT will cancel out and we are left with Vm by Vm minus B in the first term, and in the second term we have A divided by Vm RT. This Vm will be cancelled by one Vm occurring in the denominator, and let us write this in this manner, or let us now make a binomial expansion. So in the left hand side we have Z, and making binomial expansion in the first term we have and let us write this second term in the following way. It can easily be noted that this term has 1 by Vm and so does this term, and therefore we can take 1 by Vm common. This gives us and then the other terms. So this is Z, and this can be compared with the virial expansion of Z, namely this expression. Let us therefore write so comparison gives us A equal to 1, B equal to B minus A by RT. C is B square, D is B cubed, etc. We are interested with this term, which is the second virial coefficient. Now at Boyle temperature, let us find out its value. R and R will cancel out, A and A cancels out, and we have only B left, and this is 0. So the second virial coefficient vanishes at Boyle temperature. This we have shown. We now move on to the next problem. In the next problem, we have to show that the Vander Waal equation of state reduces to ideal gas equation of state at Boyle temperature for low pressure. Let us write down the Vander Waal equation of state. Which is written in molar volume. Let us take P out so that we have here, and from this we take Vm outside, and therefore we are left with this thing. So we have PVM, and we have the product of these two factors, and let us take the product. So first multiply by 1 to end up with, and then with minus B by Vm, this is RT. Let us study this bracketed part separately. We can write it as now at Boyle temperature, at low P, real gas behaves ideally, and therefore PVM can be written as RTB, and putting the value of TB, So it is simply A by B. So instead of PVM, we can substitute A by B in this expression. And this is what we get. Instead of PVM, we substitute A by B. Instead of PVM, we write A by B. A and A cancels out, and we have here too A and A will cancel out. This B will go up to make it B square, and so we have B square by VM square. Clearly, these two terms will mutually cancel out, and again this part is 0 because VM is large, it being the volume of container, and B is small, it being a correction term to VM. And here we have B square. So we can put B square to be 0 and 1 by VM square also to be 0. So we get rid of this term. And therefore we are left with 1 for this part. Putting 1 for this portion, we end up with PVM equal to RT. And this is the equation, which is the ideal gas equation. That we arrive at starting from the Vander Waal equation of state under the condition that temperature is equal to Boyle temperature at low P. So indeed, Vander Waal's equation of state reduces to ideal gas equation at Boyle temperature over a certain range of pressure. Let us come to the next problem, which states that show that the Z versus P plot at low pressure can be explained by the Virial equation of state if we retain terms linear in P for pressure. And the second question is, hence justify the role of the second virial coefficient B on Boyle temperature TB. We start with the answer. The Virial equation of state is the compressibility is Z, which can be expanded as 1 plus BP plus Cp square plus dP cubed, and the power series in terms of P goes on in this manner. And the first virial coefficient is 1, which has been written explicitly. So from here, a plot of Z versus P can be obtained. But in the question, it is given that we have to consider the plot at low P. So let us consider the low P situation, and P being low, P square, P cubed, etc. terms can be set to 0. And with this approximation, we have Z is equal to 1 plus Bp. And we note that pressure P cannot be negative. So it is non-negative, and we can assign values of B which are 0, positive or negative. So we can assign values for B such as say B is 0, B is positive, B is negative. Let us study the impact of choosing these values of B. We first discuss the B equal to 0 case. If B equal to 0, then from this virial equation, which has been reduced to two terms and is linear in P, as mentioned in the question, and here it is, the virial equation of state should be retained up to terms linear in P, and this is what we did here. So let us proceed. If B equal to 0, then from this virial equation, which is linear in P, it follows that Z is equal to 1. And then the plot of Z against P in the abscissa gives us a straight line at Z is equal to 1. So we have a straight line plot and Z versus P plot is indeed a straight line for ideal gas. So ideal behavior is depicted, and this occurs at T equal to Tb, and of course at low P, which is the assumption under which we got this equation. Let us next move on to B positive case, whence from this equation it follows that Z is 1 plus B is positive, P is positive, so some positive quantity. In other words, Z is greater than 1. So the plot of Z versus P, this is Z is equal to 1. So it will be like this. So this corresponds to Z greater than 1, and the equation of this plot is Z is equal to 1 plus mod Bp. So we see that the plot or the curve moves up and the pattern of the plot implies that it is a non-ideal behavior. And this occurs at T greater than the Boyle temperature Tb, and we are discussing the low pressure region. We now focus attention to B less than 0 case, that is B is negative. So from this equation it follows that Z is equal to 1 plus a negative quantity. That is Z is equal to 1 minus mod Bp. Here we had plus and here we have minus. So clearly Z is less than 1 in this case, and the plot of Z versus P will be, this is Z is equal to 1, minus means the slope is negative. Here we add plus, which means the slope is positive. B is the slope. Here too B plays the role of the slope. And since it is preceded by a negative sign, that is B is negative, the slope will be negative. And here the slope is positive. So this is the equation, and this corresponds to Z less than 1. Here curve moves down. It is also a non-ideal behavior. And this occurs at t less than tb. To check whether or to justify these plots, let us show the general Z versus P plot, from which we will extract the low pressure part and compare with these plots. The general Z versus P plot is of this type. This is Z is equal to 1. This is the plot for t equal to tb. For t greater than tb, the plot is of this type. And for t less than tb, for t less than tb. Let us describe these curves in terms of Z. This portion corresponds to Z is equal to 1, but this portion corresponds to Z greater than 1. This curve corresponds to Z greater than 1, and this part of this curve corresponds to Z less than 1, but the curve turns over and ultimately Z is greater than 1. Let us now identify the low P portion. Say this is the low P portion. So this part corresponds to the low P portion, and in this low P portion we have three types of curves. One is this curve, which corresponds to Z is equal to 1, which means in our previous explanation B equal to 0. So this part is actually corresponding to B equal to 0. This curve corresponds to Z greater than 1, which means B greater than 0. And finally this curve, which has Z less than 1, corresponds to B less than 0. So the curves that we drew by retaining two terms in the virial equation of state appropriately describes the low P behavior of the Z versus P plot. In view of this, we can write the low P plot, that is this region is being indicated. For real gas is reproduced by the two-term virial equation of state. And next, let us spell out the role of B on TB. as wanted in this question. The role of B was indicated before, and here it is. For B equal to 0, T equal to TB, B greater than 0, T greater than TB, and B less than 0 corresponds to T less than TB. And let us once again see this from the graph. B greater than 0 at low P corresponds to T greater than TB. B equal to 0 at low P corresponds to T equal to TB. And B less than 0 at low P corresponds to T less than TB. Before moving over to the next question, let us make a final comment. Ideal behavior at T equal to TB that corresponds to Z is equal to 1 and B equal to 0 occurs because attraction and repulsion balances. But at T greater than TB, non-ideal behavior occurs that corresponds to Z greater than 1 and B greater than 0, and this occurs because repulsion dominates over attraction. While in this case also non-ideal behavior is manifested at T less than TB that corresponds to Z less than 1 and B negative because attraction dominates. The comments written over here are extremely important and is an answer to another question, namely, why do real gases behave ideally at T equal to TB, the Boyle temperature, at low pressure? The answer is that at low pressure, at Boyle temperature, the attractive interaction between molecules is exactly balanced by the repulsive interaction between the molecules. And therefore, on the whole, it appears that molecules have no interaction. So the gas behaves in an ideal fashion. And this type of curve or line is obtained that corresponds to Z is equal to 1 and B equal to 0, B being the second virial coefficient. But if T is not equal to TB, that is at a temperature which is different from the Boyle temperature, what happens within the gas is that the repulsive interaction dominates, so there is a net repulsion, and hence gas occupies larger volume, that is expands, and this corresponds to temperature greater than the Boyle temperature, Z greater than 1, that is associated with a positive B value. And again, for temperature lower than the Boyle temperature, attractive interaction dominates, so the gas occupies lesser volume than the ideal counterpart, which means Z is less than 1, and this is associated with B less than 0. However, in this situation, that is for T less than TB, as well as for T equal to TB, when pressure is large, repulsion takes over and Z becomes greater than 1, as evident from this plot. This is the high pressure region where Z is greater than 1, and this is the low pressure region where all types of cases are possible. We come to the next question, in which we are asked to write down the compressibility values for low and high pressure regions corresponding to T equal to TB, T greater than TB, and T less than TB, TB being the Boyle temperature. We can write the Z values looking at the graph, and we answer here. Let us write T value here, then high pressure case and low pressure case, Z value, and we'll comment on the result. Here Z value, and we'll comment on the result. First, for T equal to TB, at high pressure Z is greater than 1, and the comment is non-ideal behavior of the real gas, and at low P Z is 1, and the comment will be ideal behavior of the real gas. Next, for T greater than TB, which corresponds to this curve throughout which low P or high P, Z is greater than 1. And it is a non-ideal behavior. And then comes T less than TB case. At high P, Z is greater than 1, non-ideal behavior, but at low P, Z is less than 1, which is also non-ideal behavior. So these are Z values at various pressures and temperatures. We come to the next question. Compare the following temperatures as obtained from Vander Waal's equation of state for a real gas. And the temperatures given are the Boyle temperature, which we denote by TB, the critical temperature denoted by TC, and inversion temperature denoted by Ti. And associated with this question is another one which says that how far do these temperatures satisfy experimental findings. Let us answer this question by means of a chart. First we'll take up the Boyle temperature, then we'll place the critical temperature, and finally the inversion temperature. First, the definition or the main characteristic. And Boyle temperature is the temperature at which real gas behaves ideally over a range of pressure. And this occurs at T equal to Tb at low pressure, where gas behaves ideally, and for T not equal to Tb and for T equal to Tb but at high pressure. Gas shows deviations from ideal behavior. Again, at T less than or equal to the critical temperature Tc, gas can be liquefied, but at T greater than Tc, gas cannot be liquefied. Again, at T less than the inversion temperature, gas cools on expansion, at T greater than Ti, gas heats up on expansion. And at T equal to Ti, there is neither cooling nor heating upon expansion. We next write down the expression as obtained from Vander Waal's gas. As given in the question, the expression of Tb or Boyle temperature is A by Br. That for Tc is 8 by 27 A by Br, or this is 0.3 A by Br, and that of Ti is 2 A by Br. So if we write this as Tb, then Tc becomes equal to 0.3 Tb and Ti becomes twice of Tb. Let us next write down the interrelation between these temperatures. We see from here that Ti is the largest of the three because it is twice of Tb, because this is 1 Tb, this is twice Tb, and Tc is the lowest of the three because it is 0.3 times Tb, Tb being the Boyle temperature. So we can write two things. One is that Ti is greater than Tb is greater than Tc, and secondly, let us clearly write the ratio. Ti is twice Tb, this is 1 Tb, and this is 0.3 Tb. So the ratio is 2:1:0.3. Writing 0.3 as 3 by 10 and multiplying by 10 throughout, the ratio of the three temperatures can be expressed as 20:10 1:3. Regarding agreement with experiment, let us mention that the ratio of boil temperature to the critical temperature is, this is the boil temperature and the critical temperature is 8/27 A by BR. So this is 27/8, which is 3.365. But experiments show that so this is the theoretical value. This is the value predicted by theory. And the experimental value is 2.98, which differs from this value. So there is disagreement between theory and experiment, and we conclude that Vander Waal equation fails to explain things perfectly. It definitely explains things, but not perfectly. And the theoretical values of TB, TC, etc. are not accurate. And this can also be checked or verified from the experimental values of these temperatures, as we mentioned now. Helium has inversion temperature of 24 Kelvin, boil temperature 23 Kelvin, and critical temperature 5 Kelvin, and that of hydrogen are that of nitrogen these are of course not accurate values, but just suggestive values. Let us also mention those for oxygen, we will discuss inversion temperature, critical temperature in separate videos.